Hello, welcome back. It is Wednesday, November 11th, and we are going to start off today with, of course, the joke of the day. The joke of the day today is brought to you by Bella Rowland. Her joke is, why did the gym close down? Of course, the gym closed down because it just didn't work out. Well done, Bella. Okay, let's talk about what we're doing today for your science assignment. We're going to start off with our warm-up, which again, I will be explaining that to you. After that, we're going to be completing a mini lab that says, can you model a sound wave? We're going to be talking a little bit more about those longitudinal sound waves. And lastly, we are going to be talking about the speed of sound math problems. All right, so let's get into this warm-up. Your warm-up asks, what are the 6 things listed on the decibel scale on the bottom of page 116 in order from least to greatest? Well, before we answer that question, let's ask ourselves, what is the decibel scale? What does that even mean, the word decibel? Well, here's a picture to help us with that. So this orange circle or yellow circle, whichever you prefer, act like that is where the sound is coming from. Now, let's act like my cursor is you. Okay, let's say you are standing right here next to the sound source. Well, common sense tells us that it's going to be perceived as a very, very loud noise. So think about this circle right here as like a speaker. Okay, the speaker is really loud, especially if you're standing right next to it. Okay, if we look at position number 1, they're calling that in this picture 90 lowercase d capital B, which stands for decibels. Okay, so if I'm standing here at position 1, that would be labeled there as 90 decibels. Now, the further we move away from this sound source here, you can see the lower the decibel amount. Okay, so basically, what that's saying is that the distance is relative to the loudness that you hear. Again, let's go back to our original example. Okay, act like this is the speaker. The further away you walk from that speaker, all the way out here to position 4, where it says 78 decibels, it is going to seem quieter and quieter. So it's basically like the intensity of the sound. Okay, just like if a race car, think of NASCAR. If you listen to the car, it's going to sound really, really loud whenever it's here right in front of you. And then it's going to sound more and more quiet as it travels further away from you. So that's what I mean when I say the decibel scale. So now let's look at the picture that is at the bottom of the page I told you to go to. Okay, all you need to do for your answer for this warm-up is list them in order from the smallest amount of intensity, so the lowest amount of decibels, to the highest amount of decibels. Well, obviously, over here on the left-hand side, a whisper is going to be very, very quiet in comparison to the very far right-hand side of this picture here, which is a jet plane taking off. Okay, the decibels for a whisper is going to be 15. A purring cat would be 25. And please label this on your warm-up. So you're going to say whisper 15 lowercase d capital B. So your answer would be whisper 15 decibels, purring cat 25 decibels, average home, so if you were just to be sitting at your house, 50 decibels, a vacuum cleaner 75 decibels, a power mower, as you can see in the picture down here, 110 decibels. The pain threshold is 120 decibels. So when it starts to begin to hurt when you hear the sound, if you were to be standing right here next to this jet, it would kill your ears simply because of the amount or the intensity of the sound that is coming off of that jet plane as it is taking off, which is why the measurement for the decibels for a jet plane taking off would be 150 decibels. So you have 1, 2, 3, 4, 5, 6, 7 different things that you need to write for your answer for your warm-up. It says 6 things. You don't have to list the pain threshold. That's okay. So you can just do all of the black ones here, understanding that the pain threshold is there at 120 decibels. So again, repeating this information, list the 6 things here. You do not have to list the pain threshold. Let's get into the lab for today. Okay, so for this portion of the lab, we're going to be modeling a sound wave. At this point in the year, you should understand that an example of a sound wave would be a longitudinal wave. So in order to model that, we're going to pull out our handy dandy slinky here again. You can see that I have a piece of yarn here, a piece of yarn here, and a piece of yarn here. Your assignment for this portion of the lab is to draw me a picture on Jamboard, and I'll explain more about that after I model this, of 3 different longitudinal waves. So I'm going to model here for you an example of a longitudinal wave that has very close together compressions and very spread apart rarefactions. Remember, compressions are where the spring coils are close together, and rarefactions would be whenever they are further apart. That's why we have these pieces of string here. So if I pull this long here, as you can see, again, my piece of yarn over here on the right hand side, there in the middle, and all the way over here. You can see as I pull all of these over here, and if I were to let go, it's going to go back and forth. You can see that that compression travels together and then it travels back this way. So it starts by traveling this way and then it travels back this way. One of your vocab words this week is echo. Okay, that is exactly what happens. Your sound wave travels in a compression and it hits something, whether it be a wall, whether it be if you're hiking a mountain, and it bounces back. That's why you can hear an echo. So let me model that again. I'm going to make this one a very strong, very large compression, very large rarefaction. If I let go of it, you can see that it travels back and forth. Okay, so essentially all you are going to be doing is on Jamboard, you're going to draw me a picture of a compression that is this long, and this long. Hopefully you realize that the more energy that you are transferring, the greater the compression, and therefore the greater the rarefaction. So again, let me just explain. You are going to be modeling on Jamboard. You're going to draw a picture of a compression that's pretty big, one that's medium size, and one that is small. Again, the more energy that you have, the greater the compressions, the greater the rarefactions. Okay, now that you have seen me model it, let's talk about what it is that you actually need to complete. So you don't really need to look at any of these directions because I've already modeled it for you. Okay, number 1, as I was talking about just a little bit ago as I was modeling it, you are going to be creating a Jamboard and you're going to be modeling 3 different sizes of compressions, 3 different sizes of rarefactions. Remember, we're talking about longitudinal waves, so I'm not looking for transverse waves here, like the up and down ones. I'm looking for like the coils. Okay, whenever the coils are closer together, similar to what I modeled here with my slinky, you are going to be labeling that as a compression. You are then going to label the longer spread out portion of the wave as a rarefaction. These are 2 vocab words that you've already had in the past. But again, you are going to be creating a Jamboard and you're going to model 3 of them. One that has a large section of compressions, one that has a large or a medium size of compressions, and one that has a smaller size of compressions. Okay, as well as if you have a larger compression, you're going to have more spread out rarefactions and so forth. If you have a smaller compression, you're going to have smaller rarefactions. Okay, so you're going to model 3 of those. Okay, it does not have to be perfect. I know this is not art class, so it's not that big of a deal. However, you need to model 3 of those and upload that to this post. Then you need to answer this question. It says, explain how the wave on the spring is similar to a sound wave. Well, the wave on a spring is similar to a sound wave, 1, because it models a longitudinal wave, and 2, because it models one of your vocab words as an echo. You could see that those compressions travel together back and forth, just like an echo would happen. So that's 2 different ways that a spring, in this case this slinky, could model a sound wave. So that's what you need to say for number 2. Now we need to move on to some vocab words here. I know you only have 3 vocab words, but you have quite a few options here. Okay, so we're going to go in order here, and Merry Christmas, Happy New Year. I'm going to basically give you the answers, but make sure you put these in this order that I'm giving you in order to receive 100%. This lab is still going to be 50 points. Right? So make sure you put these down. So starting with number 1. It says all, you should put sounds for that. All sounds consists of, if you look at these vocab words, hopefully you know that a sound is created by a vibration. So far we have all sounds consist of vibrations, and now we branch off here. Okay, and of course you can pause this as we go if I'm going too quickly. All sounds consist of vibrations of varying wavelengths and frequencies. Remember, wavelengths is the length between the crests or the troughs, and frequency is how many waves travel by in one given second. Remember, frequency is calculated in hertz, a capital H, lowercase z. So once again, all sounds consist of vibrations of varying wavelengths and frequencies conducted by a material. 5 is material, which can be, and these can be in any order, but go ahead and put these in this order: solid, liquid, gas. So 6 solid, 7 liquid, 8 gas. Okay, because those are all forms of material. Okay, then 6, since we put solid for that, you can put anything that is a solid. Okay, put anything that is a solid, anything that is a liquid, anything that is a gas. Okay, anything that is a solid, anything that is a liquid, or anything that is a gas. And here are answer choices up here for you, like metal, like water. Okay, those are examples, and air. Those are examples that you could put down here. And of course, that's what I want you to do. Right? So that should earn you a 50 out of 50. Again, go back and rewatch this. If I went too quickly, I told you what to put for each different one. Email me with any questions, but that should be a 50 out of 50 for you. Okay, now moving on to the last portion of your assignment for today, which is the speed of sound problems, okay, which is right here. You can see it under today's topic, which is Wednesday, November 11th. So if you click on that, click on the PDF. This is set up as a question, so you're going to have to answer it similar to how you answer your warm-up. After you click on it, you're going to see a screen that looks like this. You only have 4 math problems that you need to complete. Okay. Similar to wave speed problems, I'm going to give you 2 variables, and you are going to have to solve for the one that I did not give you. So if we take a look at this formula, S equals D divided by T, where S equals speed, D equals a distance, and T equals a time. If you look at the goofy looking formulas here, this is just the reorganized version. So if it's asking you for speed, it does not already give you speed, then you're just doing distance divided by time. If it is asking you what the distance is, you would multiply speed times time. If it is asking you what the time is, then you would do distance divided by the speed. All right, so these are the 3 formulas that are going to be your key to success here. If we look at this example, it says if the speed of sound in ice is 3,850 meters per second, how far will sound travel in 0.1 second? Well, it says step 1 here, identify the variable you will solve for. You do not know the distance because it says how far. If it asks you how far, you need to solve for distance. Therefore, you need to use distance equals, and now it's turned into a multiplication problem because it is giving you the speed, it is giving you the time, so you would multiply those 2. The second step is simply to multiply, and you know that because it's asking for distance, we need to label it as meters. So let's look at number 1. If a wave travels 30 meters in 6 seconds, well, I know 30 meters is a distance, so it is giving me D for distance. It is asking me for, or it is giving me seconds, which is 6 seconds. So I need to plug in 6 for the T. So what don't I know? I don't know the speed. So I'm going to use this original formula because I don't know the speed. It did not give me meters per second. So I need to do distance divided by time. Distance is 30, time is 6. So for this first one, I need to do 30 divided by 6. I'm not going to give you that answer, but remember your answer needs to be labeled as meters per second. Number 2, sound travels at 1,500 meters per second. Ooh, I see meters per second. I know that that is speed, so I'll plug that in for S. through water at 25 degrees Celsius. Under these conditions, how long would it take sound to travel at 300 meters? Now, it is giving me speed. It is giving me a distance. It is not giving me a time. Therefore, I need to use this formula right here where my cursor is, T equals D divided by S. I know that D stands for distance, so it is asking me for 300 to plug in for D. I know that my speed is 1,500 meters per second, therefore I need to plug 1,500 in for S. So for number 2, I need to do 300 divided by 1,500. And because I'm solving for T, I need my answer to be labeled as S for seconds. Number 3, it is giving me meters per second, so I know that that is my speed. It is asking me how far sound would travel in 0.5 seconds. So it is giving me my speed, it is giving me my time, therefore I need to multiply those because I would be using this formula to find my distance. So 331 times 0.5, and you are going to label that as meters. Last but not least, number 4, it's telling me that sound travels at 1,500 meters per second. Therefore, I need to plug that in for speed because it is labeled as meters per second through water at 25 degrees Celsius. So this one's similar to number 2. Under these conditions, how far would sound travel in 30 seconds? It's giving me my speed. It's giving me my time. I need to find my distance. Okay, so it's going to be labeled as meters. Therefore, I'm using this formula, D equals S times T. So I'm going to do 1,500 times 30 to get my answer there, and because I'm solving for distance, I need to label that as meters. I just walked you through all of that. If you need to go back and re-watch each 4 of those questions, again, make sure you're labeling those correctly and type those in as an answer like you would as your warm-up on Google Classroom. At this point in the video, let's just make sure in order to wrap up, to see that you have everything done for today, of course, which again is Wednesday. So you need to make sure you have your warm-up done. I've already gone over that. I've already given you that answer. You need to make sure you have your mini lab totally complete. The mini lab was about how you can model a sound wave. Number 3, the speed of sound math problems. We just went over all 4 of those. And number 4, if at this point in the week you do not have your 3 vocab words done, make sure you create your Jamboard in order to do that. I will be at my desk today to make sure I answer any of your questions, so please email me. Okay, tomorrow we will be holding another Google Meet in the afternoon. More details to come about that. If you already joined that on Monday, then you know what I'm talking about. But every Monday and every Thursday, I am required to have a Google Meet with you science kids on the afternoons of those days. So I'll be posting that link. Again, more to come on that. But congratulations, you survived another day of hybrid learning for my science class. Have a great rest of your day.